Okay. Hello. Can we start? Okay. So let's review briefly the set pruning since last time it was very quick. So once again, when we want to save on we want to gain in terms of lookup classification speed, we can adopt this technique. So when you start with the complete hierarchical trie, which is this one we have already seen on the left side, in order to perform this set pruning technique, the basic principle is that each trie node with a valid prefix in the first tree, the top level tree, duplicates all the rules that are in the rule set of its ancestors into its own rule set. So here, if you remember, we had rules in node A, B, D, and E. And let's go to the right side where we can see the set pruning tree. We start from A, which is the root node, and E is on the other side and has A as a only ancestor. So E will copy, will receive also rule 7, which is originally was for node A. And then on the other side we have B. Originally B had rule 4, 5, and 6. It receives also rule 7 from its ancestor, which is A. And then D has as ancestor B, so it will add to the R1 and R2, which were originally located in D, also 4, 5, 6, and 7 that are taken from B. So once we have copied all the rules in this way in the top tree, we can start producing the trees or the tries on the second level. In this case, we have only 2 levels. And so we start from R7. R7 does not get any rules from anybody else, so it remains the same as before. Then we go to R3. R3 originally had only this second level tree, and now it inherits the tree from its ancestor, which is rule 7, so we have to add this other branch, okay? Then we move to B. Originally B was formed had only this trie attached. We have to copy onto B the tree that is from rule set from A, and so you can see that we have already the white node, so the white node does not change. We have only to add the gray node, okay? And similarly with D, originally D had only these 3 attached, and this node was originally white. Now we have to take the tree that is attached to B and copy it in the same way. So this is the tree in D. Okay, you can see that now this node is gray and it has rule 7, which is taken from here. This is basically the construction with set pruning. What is the advantage of this technique is that we avoid backtracking. So when we are performing, these are the mapping as an example of the rules that are depending here from node B. So we avoid backtracking. So when we start a query, a classification process. Let's, for example, take the same as before. This is an incoming packet 001 100 in the two fields, and you can see that the path on the first field is 00 and then stops in D. Then we have to start looking into the tree attached to D in the second field 110, and we got a right directly to the final result. We don't need to backtrack because everything, all the information is already contained in this tree that is attached here. And this is another example, the second example as before, and again we find the final result immediately without needing backtracking. So this is basically this technique. And there is a special point. Let's take again another example. This is very similar to the previous one, but the set of rules has been a little bit changed. And so here you see already the final result in terms of the set pruning technique. So these are the trees that are generated after set pruning. Then we have to notice that here, when we copy the tree that is attached to B into D, we have a duplication of rules in one node, because the original rule R2 that was already present here even without set pruning, which is this one, is copied to this node. But on this node you have also to consider that there is rule 6, okay, that comes from the rules that were copied from B. So we have a collision of rules, a conflict, and we have to adopt a similar approach as we seen about IP address lookup when we talk about prefix capturing. In this case, we don't have the concept of longest prefix, but we have the concept of priority. So what we have to write finally in this node is only R2, because R2 is the rule with the highest priority, higher priority compared to R6. Sorry. Okay, so this is something that may happen when you copy rules, and the ambiguity is solved by looking at the priority. Okay. What is the complexity in this case? You can see that the storage complexity is much larger than the previous one, and if you remember, in the hierarchical tree we have only n by d by w. Now we have n power d by w, and so we have to increase by a factor of n power d minus 1, and this is due to the case that we consider always the worst case. And in the worst case, a rule may be replicated n power d times. Okay? But we gain a lot in terms of search complexity. In the previous case, in a hierarchical tree, it was exponential. Now we have only d times w, where d is the number of dimensions. And this is due to the elimination of backtracking. So when you do classification in this set pruning trie, you always do search in a single tree, which however has a maximum depth that is equal to d by w. And the complexity is also less than well, no, it's not less than the hierarchical tree, is more. It was evaluated as n power d instead of d squared by w of the hierarchical tree. Okay, so by this technique we can spend in storage complexity to gain in terms of search time complexity. There is also another possibility which allows to avoid duplication, and therefore to avoid the expansion in terms of storage capacity. So this is again the previous example, and this is the corresponding data structure that we obtain with set pruning. Now, instead of duplicating and constructing this big forest of complex trees, we can use pointers. Because basically when we are doing this operation of duplication, we are actually also merging the trees in the second level. So this tree is merged. So this tree is the original one with merged with this one of the ancestor. This is also the original one merged with the ancestors. And so instead of performing actual duplication, we can exploit pointers. Okay. The pointers are basically the links which allows to go from one node in a specific layer 2 tree to a node in another layer 2 tree, even if they are disjoint. Okay, they have different roots, but they can the single nodes can be linked by using these pointers. And this is called the grid of tries because it converts this basic structure, which is basically a tree, into a grid. Basically, for example, R7, R6, which is here, in the original set pruning construction was duplicated here 2 times. And in this case is again duplicated, but if we want to go to visit the right part, so we want to go to visit the corresponding 0 link, instead of adding a node, a link and a node and the rule 5, like in the set pruning case, we add a pointer to the rule 5, which is already here. Okay? And this pointer must have a label, which is the value of the bit of the corresponding bit, which implied in the original set pruning tree to visit the left child. In this case, when we have a 0, instead of visiting the left child, we move to this this node in the other side tree. So in this case, the tree of that we find in D is exactly equivalent to what we had in the set pruning case. And this, if you look at the book, here there is a mistake. We must have R6, because here R6 was not marked in the book, but you have it instead. The reader, again, here there are some steps where you have to be careful. For example, it may happen that you have a node, and then you may have multiple dependencies from this node. For example, okay, in this case we take this node y into consideration. So when we have y here in this position of the set pruning tree, you see that from y, in case of 0, we can move to this node, which is x prime prime. So in this case, we will have to move to node x prime. And we have to label this link with 0. in reality, you have also, in theory, the possibility of moving to this node x instead of x prime prime, because this branch here that you find in the set pruning tree was copied from this tree, but it was also copied from it was originally copied from this tree. So here you have basically an ambiguity. If you arrive here and you have a 0, okay, you may go to x prime here, or you may go also to x. In both cases, you will find rule 7 as a next case, but in this second case, you don't find rule 4. Okay. So, due to the way that we build the original set pruning case, here when we are performing the grid of tries, we have always, in this case of ambiguity, we have always to place the pointer so that we jump from one tree to the next one. Okay. If we have this ambiguity, that here we may jump to this tree or we may jump to this tree, we always choose the closest tree. So in this way, you are sure that you are consistent. Then in this tree, when you are in the position x prime, you don't have actually R7, but here you may add another link that is going to this other tree, which is the next to this one. And so in any case, you reach, you have the possibility of reaching R7. Okay. So basically, this is all you need to know to build the grid of tries. And when we are performing the classification, we have exactly the same advantage as in the previous case of the set pruning. So we don't need backtracking. In this case, that it was the first example, we find the result staying in the same trie, but assume that here you have the second field that starts with 0. So you go to D, moving with the first field 0, 0, 1, and then when you are in D, you jump to this node Y, and if you have a 0, you go to this node X prime. If you have another 0, you move to this node, which is R7, and you find R7. Okay. So in the end, there is no difference in performing the classification in terms of results and also of complexity from the grid of tries compared to the set pruning trie. Yes.
Why an X dash are physically connected, or why those two X dash to be?
Sorry?
Why an X dash are physically connected, or
These.
yeah, these are physically
Well,
connected, or
here you don't have anything physical. It's this data structure is stored in memory. Okay, so in any case, you would have pointers. Okay, so even if you do the pruning, the set pruning trie, that is these yellow circles here, when you are in node Y, you have two childs. No, one pointer with one mark labeled with 1 and one pointer labeled with 0. The difference is only logical. No, so in the set pruning trie, you keep in any case the logical architecture of the tree. So you always have a tree, because basically each node has a single input. Okay, so you can jump into a node from one input port. Let's call it logical port. This is not a tree anymore, because for example, X prime, you have two different inputs. So the topology is a grid. No? But This is again a pointer as before. Okay. Only conceptually is a pointer to another tree. It's like a shortcut, let's say. So there is no difference in terms of the implementation. These are always pointers. But the big difference is that if you measure the occupation of the memory occupation in terms of number of nodes, in this case you have less nodes than in the set pruning case, because all the yellow nodes are not necessary here. Of course, you have more links, okay, but usually links are very, if they are pointers, it means that basically they are like memory locations. So in terms of occupation, it's not it doesn't make any difference. Okay, if in the set pruning case, here when you have these yellow nodes, you have to copy what is inside the rules, what characterize the rule, which is not, of course, the regular expressions, because this is embedded in the architecture, in the topology, but for example, action. Okay, here you have to write actions for rule 7 once, twice, 3 times. If you use the grid of tries, you have only to write actions of rule 7 once. Okay. Okay, that is the difference. So in terms of storage complexity, we fall back to the storage complexity of the hierarchical trie, which is very low. Okay. And so it is n by d by w. The search time complexity is the same as the set pruning trie. So in this case, you gain on both the performance metrics. The update complexity is quite high, because you have, each time you change something in the table, in the routing table, you have to perform updates, which may be also complicated, especially if you remove a node. Then you have also to take care of all the links, all the pointers that were originating from that node. So this is basically all we can say about trie-based classification. We now move to another technique which is quite different in terms of algorithm, and this class is called a geometric algorithm, for the reason that you will see immediately. So in these geometric algorithms are also powerful, because they allow to map quite easily not only fields that are expressed in the form of prefix length, but also fields that are expressed in terms of operator numbers and ranges or intervals on the and basically ranges in a certain set of possible values. Like, for example, that the port number is larger than a certain number, which is not easily represented in the case of the hierarchical tries. So the concept is that each time you have a regular expression, no matter whether expressed in terms of prefix length or expressed in terms of operator and numbers, you can represent it as an interval on a number line. So once you decide to map these regular expressions on a certain number line, which means that you have to decide how many bits you can use to represent the maximum length regular expression for a certain field, then you can use this technique to represent any type of regular expressions. And so since here we have more fields, in each field you can identify intervals on a line number. When you combine more fields, you have rectangles or d-dimensional hyperrectangles in case you have d dimensions. But always the simplest way to understand is to think about two fields. In this case, you have two axes, so you can define a Euclidean space with two dimensions, and therefore you can represent a rule as a rectangle in this Euclidean space. So when you have a set of rules, it means that you are specifying a set of hyperrectangles. Each one is associated to a priority because all the rules are prioritized. And so in this d-dimensional Euclidean space, you have these hyperrectangles. Sometimes they are intersecting each other, sometimes they are not intersecting. But in any case, the classification process translates into a geometric problem. So the incoming packet has an header, and the header has fields with d fields, with each one with a specific value. So this translates into a point in this d-dimensional Euclidean space. So the problem of classification translates into a problem of finding which is the hyperrectangle which contains the points. And since you may have overlapping hyperrectangles, then in order to decide what is the winning one, you have to consider also the priority. So at the end, the problem is to find the highest priority hyperrectangle which encloses, which contains the point. This is not an easy problem, actually. The computational geometry theory says that when you have to solve a point location problem, in the simplest case where you have non-overlapping regions, this problem requires a complexity to be solved that is a trade-off between time and space. Okay? By space, we mean here memory. So how many memory you need to to build the supporting data structure, and by time we mean how many memory access we have to do in order to solve the problem when we are doing the classification. So when the number of dimensions is more than 3, the theoretical bounds says that the complexity can be a big O of log n in time when the complexity in space is a big O of n power d, or you can have a complexity in time which is log n power d minus 1, and in time you will have complexity which is big O of n, so linear complexity. So this is the trade-off. But this is the original geometric problem of point location. Here we are in even worse conditions because regions can overlap. Okay? So the complexity of the packet classification problem is even larger than this. And so in any case, there are some limitations. For example, if you think about a classifier with 100 rules and 4 fields, okay, complexity O, big O of n power d in space translates into a memory and a need of memory which is more than 100 megabytes. and in time a complexity that is big O of log n power d minus 1 means an average amount of memory access which is around 300. So it's quite complicated. In any case, if you don't have many dimensions, so too many fields, and you don't have too many rules, this is a nice way to solve this problem. So let's go more in depth into the technique, and as usual we consider a specific example. So here we have a classifier with a set of rules. These are only two fields. We can use only two dimensions, otherwise we cannot give any visual evidence of, of the problem. So for example, okay, so first of all we have to decide what is the number lines where we want to project the rules. And so in this case, we have a maximum length of these regular expressions, which is 3 bits. So we can take, for example, 4 bits. So here you see the two axes, which corresponds to the field 1 and field 2. And in the two axes, we consider numbers with 4 bits. Okay. So we have all the numbers from 000 to 0000 to 1111, and the same for in the other axis. Let's take, for instance, here the first rule 1. Rule 1 is 00 in field 1 and 110 in field 2. So if you identify the two projections of these two regular expressions on the two axes, rule 1 corresponds to this rectangle here. Okay. And then rule 2 is 00 and 11. And so again, if you project these intervals into the axis, you find this rectangle here, which is larger, and it's enclosing rule 1. And then here there is also rule 5, which is 0 and 10. So the two intervals are this one. Also 0 means all this interval here on the F1 axis, which is the horizontal one. And 1 means this interval on the vertical axis. Okay. Then rule 6 is 0 and 1, so it means this big square here. And so you see here that rule 6 is the big square. It's containing rule 5 and rule 2, and rule 2 is containing rule 1. Okay. These are overlapping rectangles. However, we have to consider the priorities. So rule 1 has the highest priority, rule 2 has the lower priority, then there is rule 5 and there is rule 6. When you are projecting, you are drawing these overlapping rectangles, you can identify intervals on the two axes that are defined by the intersection of the intervals corresponding to the single rectangles. Now, for example, if you take R2 and R1, okay, the interval corresponding to R2 is all this one. But then if you intersect it with the interval, let's take the vertical dimension. If you intersect it with the interval corresponding to R1, you will have two segments, these R3 and R4, small r3 and small r4. So these two segments are the projection of the intersections. And then you can do the same also on the other axis. So at the end of this process, all the two axes will be divided into segments which are not overlapping. And if you take a combination of two segments, for example, let's take this segment small r sub 0 and this segment small r sub 3, okay? if you take their combination, the two combinations identifies here on the plane a tile where you can say what is the winning rule. In this case, is rule 1. If you take R0 and R4, you identify another tile, which is this one here on the top. In this tile, the winning rule is rule 2. Okay, so the idea is that you can pre-compute before going into the actual classification. You can pre-compute all the intervals on the two axes, which are the projections of these tiles, and for each pair of intervals, you can predefine and pre-compute what is the winning rule. So basically, you can put all this information in a table, and in this table you will have as many columns as the segments on the horizontal axis, as many rows and the segments as the segments on the vertical axis, and each element of this array will contain a specific rule, which is the highest priority rule for that specific combination of intervals for that time. All these can be pre-computed. So once you have received the packet and you do the classification, all you have to do is to find out what is the pair of intervals in which this point falls. And for example, here, if you receive this packet corresponding to this point P, this will be in R3 and R0. Then you go to the table, which is pre-computed with R3 and R0, and you find the corresponding element, and this will directly tell you that the winning rule is R1. Okay, so you have basically just one access to the array. And the good thing is that you can perform the identification of the segments that corresponds to the received packet one dimension per time. So you can do first identification on this axis and you will find out R3. Then you can do it on this axis, you will find out R0, and then you combine the results. So the classification problem translates, which is d-dimensional, translates into d one-dimensional classification problems. So this is another example. This is a classifier which is similar to the previous one, but with some changes. Here the line number is considering only 3 bits, so you can do it all the same. And the right packet contains 001 and 110 in the two fields, so you identify the incoming packet as belonging to the second interval here and the first interval here. Then you go to the table and you will find the result for this tile, which is R1. Okay, but actually the first interval on both the dimensions corresponds to this tile, which is R1. And you already know that is R1 because you solved in advance the overlapping problems by comparing the priorities of the rules. This is called a cross-product algorithm, and so it works by performing d range lookup operations, one on each field, and then you compose the results in the pre-computed table, and then you have the result that is the highest priority rule, which is matched by that specific packet. And so the complexity also depends on the lookup complexity also depends on the complexity of the lookups of operations in each of the dimensions. Because once you have the result in terms of the two tuple of coordinates into the array, then you have the result immediately. So this is again another example, and it also tells you how to build the the base structure. So the first we first take the rule specification in F1 and F2 fields, project them into the line numbers. In this case, we are again using 4-bit line numbers. So we identify all the non-overlapping segments or ranges, and then for each of these ranges, we will identify a tile here where we know what is the winning rule. Okay, this is already calculated here in the array in the table, so in the plane. So you can immediately build the pre-constructed table. Basically, this element here in the bracket is one of the is the row number that you find in the table. This is the column number, and for each row and column you will have an element which is has the value that is written in this scheme here. Obviously you need an array which has as many elements as the number of rectangles that are not the original rectangles representing the rules, but the rectangles that are obtained by the intersections of the original rectangles. So here you have only 7 rules, but the number of rectangles that you have here in the plane is much more, because you have all the overlapping regions and the intersections. So once we receive the packet, we have to perform the lookup operation in one dimension and in the other dimension. In this case, for example, we receive the packet with this value, the red of the first field and the blue in the second field. First, you do a search into the first line number, the horizontal, which represents the first field, and then you find that 0010 belongs to the segment which corresponds to, which was named R sub 10. And then we do the same in the vertical dimension. We discover that 1100 belongs to the segment R sub 2 of parameter 3. And so we have to go to the table using 0 and 3. So we look at column 0 and row 3, and we find in the table the result, that is R1. Okay, that is the best matching rule. Questions? This is again the other example with only 3 bits in the number lines, and this is similar. So this is the packet received 001 100 110. It is this point that corresponds to this red rectangle here, red square. The red square is inside the green tile. The green tile corresponds to the element R sub 2 4 and R sub 2 sub 1 1, and so you go to the look into the table with these couple of this pair of values, and you find again the pre-computed best rule, which is R1. What is the complexity of these? What are the performance of these algorithm? The storage complexity, of course, is depends on the number of tiles that are created by the intersection of the rectangles that are created by the rules. And so it was proven, there is a theorem that says that if you have regular expressions in the form of prefixes, which is one special case but frequent, and you have n prefixes, the intersection of the rectangles that are generated by these n prefixes can define on each dimension, so on each line number, at most 2n minus 2 ranges. So the segments, the number of segments is 2n minus 2. So if you combine all these ranges, you obtain a pre-computed table size, which is basically goes as a big O of n power d. So the complexity in the storage performance is exponential with the number of rules, okay? And the exponent is the number of dimensions. Instead, in terms of search complexity, here we are much more effective because it only depends linearly on the number of dimensions, and the factor by which we have to multiply d is the complexity of the lookup operation in one dimension. Okay. So it depends really on the lookup operation in one dimension. The update complexity is quite high because each time we change only one one entry in the routing in the classification table, we need to again reconstruct everything because we have to take into account all the overlapping situations, so intersections, and so you can have much different let's say content in the table each time you change something. So each time there is an update, the table must be recomputed from scratch. There is an alternative, or let's say a variation to this method, which is which exploits bitmaps. So the bitmaps are basically data structures that allows you to represent a certain Boolean variable or a set of Boolean variables that, and each specific variable corresponds to a position in a binary number, a binary digit position in a binary number. So we start again with a representation of the rules in terms of overlapping rectangles in the d-dimensional space. Let's take again the two-dimension case because it's feasible. And so again we start identifying on the two axes the set of intervals that are generated by the intersections of all the rectangles. And for example, here we have these overlapping rectangles of rule 1, 2, 3, and 4. They intersect in various ways, and so they generate on the x-axis or horizontal axis, they generate these segments from 1 to 6. On the vertical axis, segments from 1 to 6 again. Okay. And now we take each of these segments, let's say x1, and then we go on x1 to explore what happens for all the values of x1 to the rules that are let's say overlapping with the rectangle, the infinite stripe, let's say, that you take by considering this interval x1 on the horizontal axis and all the possible numbers in the vertical axis. And for example, here you see that if we take x1 this stripe, then on this stripe we will have rule 4 and rule 3. Okay, rule 4 and rule 3 have a region of validity on this stripe, while the other two rules, 1 and 2, don't have any validity region on this stripe. So we produce the bitmap this binary number you see below x1, and in this number, each bit, the position of each bit corresponds to a specific rule. So the number of bits of this bitmap is equal to the number of rules that you have. Okay, here we have 4 rules, so we have 4 bits, and rule 4 is satisfied on this stripe, so we mark it as a 1 in this position. Rule 3 also another 1. Rule 2 and rule 0 are not satisfied, so there will be 2 zeros. And another important thing is that since all these rules have a priority, when we are making the rules corresponding to the bit, we sort the rules in a priority order. So, for example, let's say that 1 is the highest priority rule and 4 is the lowest. So the first bit will be corresponding to 1, the second bit to 2, the third to 3, and so on. Okay. And we do the same on both the dimensions. So this is for dimension, the horizontal axis, and this is for the vertical axis. Here there is rule 4, which is highlighted, is in green, and you can see on the two axes what is all the values of 1 that corresponds to the interval of validity of rule 4 on the 2 dimensions. And all these bits occupy the 4th position, okay, because this is dictated by the priority of the rule. So this is again all pre-computed. Once you have all the rules, you can pre-compute this set of bitmaps for each interval. And so what happens when we have to do classification? We have a packet that arrives. It will have 2 values for the 2 fields, P1 and P2. So again, we do 2 separated lookups, one for the horizontal dimension, so F1, and the other one for the vertical dimension. And then we find out the 2 segments. So, for example, let's say X1 and Y1, the 2 segments which corresponds to the incoming packet, that are matching with the incoming packet. And then instead of looking into the table as we did before, we do a simple operation of combination of the 2 bitmaps. So we do a bitwise AND between the 2 corresponding bitmaps that we have identified. And since we have sorted the rules in order of priority, we can find directly the result. What is the result? The result is the rule that is corresponding to the first one from the left of the resulting binary number, which is the result of the logical AND operation, because it is basically is the rule that is matched on both the dimensions and which also have the highest priority. So that is the result of our lookup operation. So if we don't want to have this pre-computed table, we can pre-compute the bitmaps. And we obtain directly the result by doing an AND bit by bit. So this scheme basically is an alternative to what we have seen before. It can apply to multidimensional packet classification. We can use fields that are specified with any regular expression, both in terms of prefix or in terms of intervals. And it is again based on the observation of the rules that are matched in each dimension that are then combined to find out the final result. The complexity of the bitmap is, in terms of storage complexity, not very different from the previous one. Here, but actually we don't have let's say the the table, the array, but here we have bitmaps. So if we assume that since each bitmap is n bits wide, because we have as many bits as the rules, so the dimension, the ranges on each dimension is in a large O of n, as we have already mentioned before. The final storage complexity would be d multiplied by n squared, if we have d dimension. Search time complexity, again, it depends on the lookup operation that you perform on a single range, which is t sub rl. This is multiplied by d because you have to make d lookup operations. And then there is this factor, this additional factor, that is depend on the memory width and again the size of the bitmap that you have to consider, which is basically n bits. So compared to the previous case, we can reduce the time complexity by a factor of d because we look up at each dimension independently. And the update complexity again is quite high because each time you add a rule, you have to recompute all the bitmaps again from scratch. And here, for example, you have if you have 512 rules, and you can classify up to 1 megapacket per second using FPGA and 5 megabyte SRAMs. Okay, so this is basically about the bitmap. Then also heuristic algorithms are questions. Heuristic algorithms are interesting, but we skip them because they are quite complicated. We don't have so much time. So the final packet classification technique is based on the TCAM. This is something that we have already seen by talking about IP address lookup. And the TCAM works basically very similar to what we have seen in the IP address lookup. So in the core of this hardware implementation, we have the TCAM here, where we encode, we store the rules, so the regular expressions, and and then we have a RAM where we store the actions. In the IP address lookup case, here we stored the information about the next hop. Now we have to store actions, which are more complicated, but still the concept is the same. So once you arrive to the TCAM with the received header, which is used as a search key into the TCAM, then you find a set of matching rules, as we found a set of matching prefixes in the previous case. There must be some way to arbitrating between the rules, considering priority. Then you will have a winner rule, and the winner rule will send a signal to the corresponding action, which is stored in the RAM. But in this case, we have something more complicated, and in particular, not necessarily we can use, or it's good to use the received header directly as a search key into the TCAM. Okay. Because again, we can directly represent in the TCAM all the rules that are expressed in terms of a prefix regular expression. But we have problems with the rules that are expressed in terms of intervals. And in particular, so for rules that are expressed in terms of prefix, we can use the value and mask pair that we have already introduced before for IP address lookup. But what happens with range matching? We have, if we want to map directly ranges into the TCAMs, we have these, to perform this operation of range splitting to convert ranges into set of prefixes, into set of prefix originated ranges before sending them to the TCAM. And this increases the number of entries by a factor which is estimated to be W power D, where D is the number of dimensions. So if we have a range that can be exactly implemented in the TCAM, then it's good. We can use directly the value and the bit of the bit mask in order to define the mask operation. But if we have a range, this is not very nice. So for example, let's take this range here, which is typically applied to the their 4-port number field. For example, this range is the number is greater than 1023. That in binary means that the number is greater than this binary number. If you translate it into regular expressions in the form of ranges, you have the range splitting phenomenon. Because, first of all, you have to consider the range between 1024 and 2046. This is the first possible range. But then you have the range between 248 and 595, and so on and so forth. So if you want to translate this expression into a prefix-based expression, you can do it in principle, but you generate 6 subranges. Okay, so once you have these 6 subranges, each of these 6 subranges should be mapped into an entry in the TCAM. So this is why it's not very efficient, because you multiply the entries of the TCAM by a high factor each time you have ranges. So if you only consider this range here, that is what you would guess by looking at this number, this is not actually enough, because it only includes this interval, but you have to go to consider all the other intervals until the end. So this one and so on. So this means that you reduce the memory efficient due to range mapping, and this means higher power consumption, larger TCAM, and higher cost. So the solution is to adopt pre-processing or encoding operation before writing an entry into the TCAM. If it is a range, then it is treated in a different way compared to the regular expressions that are based on the prefix format. And this is called rule encoding. This can always be pre-processed. So we can view a d-tuple of rules as a region, a single region in a d-dimensional space. And then we can encode the overlapping regions and then translate the rules in a sequence of encoding bits. Since we are doing a rule encoding, we have also to encode the search key. So instead of taking directly the values of the fields that are coming from the packet, we have first to process these values in order to transform the values into a search key which is which encoding matches the rule encoding basically. Once we have done these two encoding operations, then we can use the TCAM in the regular way to find out the result. So when we have the TCAM, we can adopt this efficient scheme, efficient mapping scheme, in order to avoid the expansion of the entries. And we have to, however, then organize the way the rules are stored. So for each field, we have to define for each range field, so the field that is expressed in the similar way as we have seen before, we will define an n-bit vector that is this vector here, where n is the number of distinct ranges that are specified for a specific field, and b is the vector of ranges. So each time we have a rule that is an incoming packet that is matching one of these ranges, then the bit in the corresponding position will be set to 1. And so if when we are doing when we are storing this information into the TCAM, we will set a net mask with a 1 in the position that is corresponding to the specific range that we want to encode in that specific entry in the TCAM. Let's take an example as usual. So this is a classifier where we have two fields, yes, two fields. One is the destination IP address, so it's already expressed in a form of a prefix and prefix length. And then we have the destination port range. So in this case, for example, we have the first range, which is greater than 1023. Then another range which is between 50 and 2000. Then another range that is equal to 80, and then equal to 23 and equal to 21. So instead of translating each of these range into a prefix form formulation that will require an expansion of ranges, we do a rule encoding so that in the TCAM we add these columns, and in each of these columns we have all zeros in the mask and a single one in the mask corresponding to the specific range. So for example, here we have the first entry, which is destination IP address that is matching with 10/8, combined with destination port, which is greater than 1023. So in the TCAM, we will implement this rule by using the first columns as a regular expression based on prefix. So in the first columns, we will write 10.0.0.0 as value and 255.0.0.0 as mask. Okay, so basically here you have a 10, and then each time you have an X here, it means the value does not matter. Okay, in this case the X refers to an entire byte. Then on the other side we have a final one, and then 4x, other 4 x's. These are the columns that corresponds to the encode the second field. Why we use 5 bits here? Because in this field we have defined 5 possible ranges. The first range is greater than 1023. The second range is between 50 and 2000, and the The other three ranges are 80, 23, and 21. Okay, so equal to 80, equal to 23, equal to 21. So you don't, here you find directly the regular expression that come from the regular expressions which come from the rules. Here you don't find directly the regular expressions coming from the rules, but you find the coding of that regular expressions. And the coding is similar to what basically using a bitmap for that regular expressions. So what happens when we have to perform the classification? So when we have to perform the classification, we receive an incoming packet with a certain header. The header has this set of it has a set of values for the field, and we take the field that is corresponding to the field where we have ranges, and we transform it into an n-bit vector. This n-bit vector contains as much bits as ranges that are defined. And when we do the classification, before doing the lookup into the TCAM, we have to encode the incoming packet so that when we take the value of the second field, in this case the port number, we transform the incoming packet header, the value of the incoming packet header, into this bit string. Okay? And in doing this transformation, we have to check if the value of that field falls into the ranges that we have defined. So if it falls into the first range, we will set the first bit to 1. If it falls into the second, we will set the second bit to 1, and so on and so forth. If it is not included in a specific range, we will set the corresponding bit to 0. So we can we have to translate the incoming packet in a similar way as we translated the rules. Once both are translated, then we can do the TCAM operation. So we can look into the TCAM. So this is basically it shows how we can implement the classification, the encoding of the incoming packet. So these are the ranges, the original ranges that we have defined in field number 2, the destination port. This is the way we have encoded the ranges into the TCAM. And now we have correspondingly to encode the incoming packet. So the incoming packet will have a number which is the 16-bit port number. We have to use this number as an address into this memory, which is RAM. It's a simple RAM. We don't need a TCAM. And in this memory, for example, here we have the range greater than 1023. So we set the first bit to 1 for all the values that are larger than 123. Then there is the other range that is between 50 and 2000. So we set the second bit, this one, to 1 for all the values that are complying to this condition. And you can see that we can have values with more than 1 bit set to 1. Okay. The other bits are 0 because they are not complying the other conditions. Which are the other conditions? The third one is equal to 80. Then we have equal to 23. Then we have equal to 21. So here we will set the third bit to 1. Here we will set the fourth to 1. And here we will set the fifth to 1. Okay. So when we take the incoming packet, we extract the content of the second field, and we use it not directly to look into the TCAM, but first to look into this RAM. And this RAM is basically an encoder which will translate it convert it into the content that we have corresponding to the position. So let's assume that we receive, I don't know if there is an example here, but let's assume that we receive a packet with destination port number 79. It will be translated into 00010. Okay. Then this value here is used to look into the TCAM. And so then basically we have the result, because if the incoming packet matches the specific rule, then let's say that it is 78, 79. So we will use 00010 to look into the TCAM, and it will match only with rule number 2. Okay.
Fixed.
It's fixed.
This will
Well, fixed, it means that once we have the classifier, we have defined the rules and all the regular expressions, the encoders are fixed. Okay, we can fix both the encoder of the rules and the encoder of the incoming packet. And the implementation is very straightforward. It's a simple run. Okay.
but this we understand that the binary 0 1. So if the packet is a random packet with some uncertain value, so what you are saying is like it will automatically be translated into 79, or it can fit into anyone.
No, the incoming packet would have 79. The incoming packet for this field, this is the port number. So in the incoming packet, it corresponds to a 16-bit binary number. Okay. In the RAM, you have obviously you must have 2 to the 16 positions. So you can use that incoming bit, that incoming value, as an address to look into this table, into this RAM. Then once you look into this RAM, you convert that value 79 into a bitmap with 5 bits, which is 00010. This value is used to look into the TCAM, because in the TCAM you will have this set of columns, and if it is 00010, it will match with rule number 2 for this specific field. Okay. We can make another enhancement if we want, that is even more performing, and this enhancement is possible each time we have non-overlapping ranges. In the example that we have seen, this is overlapping with this, so you cannot adopt this technique, and 80 is also overlapping with this, but 80, 23, and 21, better said, equal to 80, equal to 23, and equal to 21, they are non-overlapping. They are mutually exclusive. So if a number is equal to 80, it cannot be equal to 23 or 21. So instead of using 3 different bits to encode these 3 rules, we can do a compression, and we can do a further encoding, and so we can use a number of bits which is log 2 n plus 1. Okay, so basically instead of setting bit 1 bit, so in this case, instead of using 3 bits, that should be for a rule for 80, 23, and 21, we can use only 2 bits. And if the two values are, if the value is 0, it means 80. If it is 1, it means 23. If it is 10, it means the other value. So this is the example. This is the original TCAM that we have constructed so far. And so instead of using 3 bits, since these 3, the corresponding 3 intervals are mutually exclusive, we can use only 2 bits. Okay, and the value 0, 1, 1, 0, 1, 1. Obviously, we have to do the same also when we are encoding the incoming packet. So we have to split the incoming packets and encode them using the similar encoding. So let's say that we have received a packet with these two values. So this is the first value, and the port number is 80. Then 80 is a number which is matching with equal to 80. So we have 0, 1 here in the encoded part. And it was also matching the original rule, which is between 50 and 2000. And so this is what we have after encoding. Then we can use it to look into the TCAM. Okay, so this is the value 10 was because 80 falls into the range between 50 and 2000. And the value 01, it is because 80 is equal to 80. And so we find the matching again, but using a reduced number of bits. So that basically the 6 bits that were original, so 5 bits originally needed are now reduced only to 4. So the storage complexity is reduced because we reduce the number of bits that are of columns of the TCAM, and we can accommodate a much larger number of rules. However, again, when we are doing the addition or deletion of rules, we have to recompute the translation tables. And so this is the update complexity is quite high. So this is basically the end of packet classification. So on Friday, we will look at some exercises on packet classification, similar to what we did on IP address lookup. And this basically concludes this part of the course. And then in the rest of the course, we will talk about buffering. But this part of the course, based on that considers IP address lookup and packet classification, is what you need to perform the projects. So you can start working on the projects by just after. Next week or on Friday, I will also review the groups, so we can conclude the group formation. Okay, thanks.